All right, good afternoon, everyone. I think we should start. So just a reminder, we have our due of the midterm project report on this Friday. So I just want to clarify again, because some students expressed concerns about the midterm project report. We don't require you to succeed in doing your research. That's not possible. That's not guaranteed. So just want you to show a kind of like a decent and comprehensive procedure using probabilistic learning techniques to explore something in your research project. I mean, if you're not doing paper reading project. So the midterm project report just asks you to summarize what you have done so far. Of course, you cannot just say, okay, this is my problem I want to address. I collect some data. That's not sufficient. At least you should run like one or two baseline algorithms and show the results and express your give the summary of the current results and what you're applying for the next step. That's it. So it's not too much. So don't feel over concerned about that. But don't do nothing. you should do something on that. Does it make sense?
You have to submit the code?
No. Don't submit your code. I mean, in your final project report, you should give some link to your code repository like GitHub. And you are free to like release your code. I mean, make it open publicly or use private. But if you choose to be private GitHub reports, just to give the access to our TMs. They're going to take a look at that. That's all. Any other question?
Is it possible to put the code of the homeworks on GitHub publicly?
Yeah, you can do that. Yeah. I mean, actually, you can post it. I mean, we're not too much worried about like some. I mean, other students are gonna plagiarize your code, whatever. We have our own system to check the. You cannot like it's not like the just copy the previous people's code and without any modification. There's a lot of system doing that. So yeah, feel free to do that if you feel good about that. Any other question regarding the homework? And oh yeah, and by the way, we have extended the homework too, because we received a few requests for the extension, not too many, but considering that quite a few may also busy with other classes, especially midterm exams, so we extend the deadline to today. That means you still have 2 late days, but if you have already submit your assignments on Tuesday, that's the urgent deadline. You'll get like 15 bonus points. That's not bad for you. Right? But if you want to pull out your code and make some check and submit today, that's fine. It's totally up to you. But I mean, our homework 3 has been released, so do not hesitate. You can do it right away. And the workload for homework 3 is not huge at all. You don't have any programming assignments on that. Just a simple check of your understanding of the probabilistic graphic models. Okay, so let us continue with the variational inference. So in the last lecture, we first introduced the EM algorithm, and with the Gaussian mixture model as an example. So Gaussian mixture model, essentially, you can view as a probabilistic version of k-means or clustering algorithm, right? We use a probabilistic sampling procedure to model how we're going to generate the clustering assignment or membership variables for each data points. And given each data point, we given the cluster assignment, then we sample the whole data point, which is vector, through some cluster specific Gaussian. Right? So that's why we call it Gaussian mixture model. Of course, if you don't like Gaussian distribution as your cluster specific sampling procedure, you can choose others like T distribution, like you can have like any mixture of mixture models based on different basic distributions. And the learning of the Gaussian mixture model is based on the so-called EM algorithm. So yeah, maybe let me go back to the algorithm framework for the EM algorithm, right? So okay, so this is a EM algorithm. So you can basically view EM algorithm is a kind of like alternating update algorithm. It has a basic assumption that so theta here indicates the hyperparameters of the model, right? In the Gaussian mixture model, it corresponds to the cluster specific mean and the covariance, and also the probability vector that your data point belongs to any of this cluster. So if our goal is to maximize your likelihood of the data or marginal distribution of data given those hyperparameters. So one way of doing so is to directly maximize this model evidence, which we call this model evidence. But it has issues, at least in Gaussian mixture model, it has like singularity issue. Right? So when you're in the initialization of some cluster center close to or overlap with one data point, then that whole cluster is kind of collapsed onto that point. We have explained that issue before. So, and in other cases, it will be possible that you even are not able to give a closed form of this log model evidence. So the EM algorithm instead wants to estimate or calculate the posterior distribution of the latent random variable given data, and also update the hyperparameters jointly. So this is so-called EM algorithm. Right? So it basically in each iteration, given the current parameters, which we call theta O, we first calculate a distribution Q of Z, which is essentially the posterior of the Z, given the current data and current model parameters. And then we substitute the current posterior for QZ in this lower bound of the model evidence, right? So remember, when we talk about lower bound of model evidence, this is important structure, right? Through applying the Jensen's inequality, we know that the log model evidence is equal to this guy, which is essentially a function of the model parameters and some third-party distribution over Z. Right? And then plus the KL divergence between Q of Z and the posterior of Z given X and theta. Right? So this can be easily verified. And this lower bound essentially is a expectation with respect to Z. Take the logarithm of this fraction between the joint distribution over the Q of Z. That's it, right? So we often refer to this lower bound as evidence lower bound, a model evidence lower bound. So the good thing is that from this structure, we can see that when you take Q of Z to be exactly the same as the current posterior, given theta, your KL divergence becomes 0, right? Then that means the lower bound reaches the log model evidence. That actually motivates the EM algorithm, right? So it serves a bridge. Right? So at any step, right, given the current parameter theta, you can calculate Q of Z from this posterior distribution. Right? Now you just shove this current posterior distribution into this lower bound and fix it. That means you fix this part. You only will the remaining theta as some free parameters. Then you maximize this lower bound. You end up with a new lower bound. Right? And of course, because you're maximizing this function, your new theta will always give up a better lower bound than old theta. Right? And this new theta, of course, the lower bound will be upper bounded by the log model evidence based on this new theta. And meanwhile, we can observe that we take old theta and the posterior calculated based on O theta, your lower bound reaches the old model evidence. So now you can, from this inequality, you can see actually your new theta indeed improves the marginal data distribution or the log model evidence, but you never need to explicitly maximize this model evidence. You just maximize an intermediate surrogate. So in general, the EM framework will be like, okay, every time starting from the current model parameters theta O, right? You calculate Q of Z as the posterior distribution of your latent variable Z given X under the current parameters. Then you plug in this Q of Z into your lower bound, right? And fix it, and fix all the parameters in this Q of Z as constant. They have nothing to do with theta. Now you maximize the lower bound with respect to theta only. You got your new update theta new, right? And then through the analysis in the last lecture and also what we have just reviewed, we know that the log evidence on the theta new will always be no less than the log model evidence on the theta O. Right? So that's the idea. And as someone has already has also pointed out, this is essentially a coordinate updating approach, which I agree. So you can view, well, your evidence lower bound is parameterized or determined by two inputs. One is the theta, the other is the distribution over Z. Okay? So the EM algorithm is like, okay, I'm gonna fix theta, then I optimize L with respect to Q of Z, which more rigorous speaking should be will as functional maximization. When you do this maximization, you see that the maximum will achieve when you take Q of Z to be the posterior. And at that maximum, the lower bound will become the true posterior. Of course, given the current theta. And next, we're going to fix Q of Z and then update theta. And in this way, we kind of further improve this lower bound. And this lower bound on the theta new is upper bounded by the true model evidence on the theta new. So then from the same chain of the inequality, you see that the log model evidence on the theta new will definitely bigger than or less than, bigger than or equal to the model evidence or theta O. So that's the whole idea. And then we use the Gaussian mixture model as an example to showcase how this EM algorithm can be applied. And we listed all the updates equations. I'm not going to repeat, but I highly encourage you guys to derive this. It's not hard, given you're all experienced in deriving the gradient of this matrices and vectors. So it's pretty standard, and I believe. And we also showcase some running examples of algorithm. If you're interested, you can try to implement GMM by yourself. It's not hard at all. And then grab some simple data sets and check how this Gaussian mixture model is working. It's actually it's pretty similar to what K-means algorithm is running. Like you see that the cluster center is kind of more and more reasonable, starting from some random initializations. At the same time, the benefit of using Gaussian mixture model is that it can also give you like a cluster covariance, which not only can help you quantify the uncertainty, right? At which probability this particular data point belongs to cluster 1, cluster 2, cluster 3. You can compare with them. Also, we can have some kind of sense that what is the range of this cluster. Okay, so now we're going to talk about the global variational inference. You see that the variational inference, the whole framework is actually share the same framework or decomposition structure of the log model evidence that YAM algorithm uses. So it's just a more, it's kind of more general version of YAM algorithm or relaxation of the YAM algorithm. So I think we have reached to this point in that YAM algorithm, the basic assumption is that, okay, at each step, I can always compute the posterior distribution of the latent random variable given the observed random variables under the current model parameters. Right? This is actually a very, very strong assumption. Because in general, if you want to compute the posterior distribution of any random variable, right, you have to apply the base rule. Right? So the Jordan distribution divided by the marginal distribution, where the marginal distribution of data is an integral. Right? And in most cases, this integral either does not have an analytical form or is high dimensional and intractable to calculate. Right? So, except a few simple cases like Gaussian mixture models, like Bayesian linear regression, in most of the cases, you won't be able to find the denominator when you apply the base rule. Here we just give one example, like it's just low dimensional, it's just scalar. Right? Suppose your z is just a scalar, the prior of z is just standard Gaussian, but the likelihood of z of the observed label given z is a logistic regression. Right? So you transform z through some sigmoid function and use that as the parameter that determines the Bernoulli likelihood. Even doing that, you cannot compute the posterior distribution of z given x. There's no analytical form for that. So, of course, we want to be able to compute any probabilistic models. Right? We do not want to restrict ourselves to some simple family of models like Gaussian mixture models, Bayesian linear regression, and so on. Right? We want we want to find a kind of like a very broadly useful approach to calculate approximate posterior distribution. Right? So that's one major motivation of the variation inference. So here I want to highlight the key idea of the variation inference. Again, although we have read through these lines in our last lecture, at the end of our last lecture. So the basic idea of the variation inference is that, okay, now that in general, the posterior distribution, arbitrary posterior distribution given z under x, given x, you don't know its form. Right? It might not have any closed form. Right? You don't know how to accurately calculate the density of posterior probability. So then to sidestep this, right, we're gonna pick up some type of distribution to approximate. Right? So since I don't know this form, let me just assume this is a Gaussian. And this might be like very rough, very close, very assumption. Right? But let's just try to approximate with a Gaussian. Right? So, and then you can designate a family of Gaussian distributions as the range of approximation come from. Right? And of course, your true posterior, the ground truth, is very likely to stay outside of your approximation family. Then my goal becomes, how do I, from this approximation family, find the best one?
Do you have access to sample problems?
No, you do not have access. That's a very good point. That's why what I said right now is kind of conceptual ideas. And then we need to address, how do we measure the closeness between any approximate distribution and the true posterior distribution? And in a sense, and under the fact that you actually do not know what exactly the true posterior is. Okay. But let's just take this idea first, right? So the idea would be, okay, let me specify a family of a simple form of distribution. Right? like a Gaussian family. And then the goal is to find the best member that is closest to the true posterior. Like from this figure, we can imagine that you might choose a Gaussian here, right? And it looks like it will be the closest to the ground truth posterior distribution. And very roughly speaking, you can view this as an optimization problem. Right? You're trying to optimize the distance or the closeness between the ground truth and the approximation, the members in the approximation family. Right? That's the idea of the variational inference. It essentially converts the integration problem. Right? Remember, if you apply Bayes rule to calculate the posterior, you are actually needs to address a integral problem, integration problem. Right? So now, by introducing the idea of variational inference, your problem becomes an optimization problem. Right? You want to optimize the member, a particular type of approximation distribution in some designated family, right? To make it as close to the target posterior as possible. So take a concrete example. Look at the example just mentioned. Suppose this is your probabilistic model. You got your latent random variable z, sampled from a Gaussian distribution, and you have observed a binary label, right? Binary data either 1 or 0. And given z, the x is modeled by this logistic regression likelihood. Right? And our goal is to compute the true posterior of z given x. Right? Of course, we don't know the exact form of this posterior. Right? So, and we're going to use some variational approximations. That means we might choose Q of z to be a Gaussian distribution. And then the task would be how to determine the best mean and variance in your approximate Gaussian posterior. Does that make sense? Yeah. That's the basic idea. I mean, you might feel like, okay, I don't know. I even don't know where is the true posterior. How do I find who is the closest to him? Right? But actually, we can do this. We can do this. Okay, so suppose we now have assume a family of approximate posterior Q of z. It might be Gaussians, or it might be a mixture of Gaussians, or it might be T distributions, might be Dirichlet distribution, or whatever. You're free to decide the family of approximate distributions you want to use. And then first, to find the best approximate distribution to the ground truth posterior, we need to come out some like measurement about the closeness, right? And how do you measure the closeness between two distributions? And based on that kind of measurement, you can minimize that kind of measurement to ensure you're optimizing your approximate posterior distribution. Right? So a commonly used measurement is called KL divergence, which we have discussed before. Right? This is very, very important. You see, in machine learning area, KL divergence is everywhere. But basically, you can roughly will like KL divergence is a kind of difference between two distributions, but you shouldn't will as distance because KL divergence is not symmetric. Like KL between P and from P and Q usually is not equal to KL from P to Q to Q. But I mean, there's no perfect things, right? KL divergence as compared with other type of divergence is usually much easier to compute. And if you want to seek for a better, seemingly more perfect divergence or distance between distributions, there are a lot of choices. But people will usually choose KL divergence for pragmatic people. That's for pragmatic choice. Like, and there are more I would say more abundant family of divergence is called alpha divergence, while Kerr divergence is just one instance of the alpha divergence. There's some kind of research along that direction. How do you minimize alpha divergence between the target posterior and your the proximate posterior? Well, that's kind of research topic, but right now, let us assume, okay, we're going to use Carroll divergence to evaluate the distance, not distance, the difference between your approximate posterior and true posterior. Right? Then our goal, if we index our approximate posterior by alpha, then our goal is to minimize the Carroll divergence between your approximate posterior and the true posterior. That's the framework. But of course, there's some issue here. Someone has brought up this issue. Right? So we actually do not know the true posterior. Right? If I really know the true posterior P of z given x, why should I do this variation inference? I can just use it. So then there comes a problem, right? Can we find a way to minimize this without explicitly computing the true posterior? If you can find a way to sidestep the computation of the true posterior, but you're still doing this minimization thing, then we can conduct our variation inference idea, right? We can fulfill that idea. Right? And the key trick to sidestep the direct computation of the Carroll divergence is based on this decomposition of the mod-evidence. So remember, when we talk about the log mod-evidence or log evidence, let us first assume the hyperparameters are fixed or no. Right? We can put it aside. Right? So that means mod-evidence can be written as a summation between the lower bound and the Carroll divergence. So the lower bound is determined by a third-party distribution Q of z. And the Carroll divergence is between Q of z and the true posterior. So since we have already assumed all these hyperparameters are fixed are known, so this log mod-evidence will be fixed. And this decomposition tells us this fixed evidence essentially is a summation of this lower bound determined by the third-party distribution Q, which can be viewed as a variational approximation. And the Carroll divergence between this Q of z and true posterior. That means if you maximize the lower bound, it is equivalent to minimize the Carroll divergence, right? Because the total summation is fixed. Okay. So now kind of like convert this problem to maximizing this so-called variational lower bound. And then we can take a look at the variational lower bound. You can see that this is the expectation, right? So expectation under Q of z. And the thing you're going to take expectation is this logarithm of the fraction between the joint distribution and Q of z. So the joint distribution is always feasible to compute, right? Because once you have identified a model, design a model, you're able to write down the joint distribution. This is always feasible to calculate the joint distribution, the joint probability density. Right? And if your Q of z is not that crazy, right? Because we usually assume your Q of z from a simple family of distributions. Right? And then it is possible to efficiently maximize this lower bound. And when you maximize this lower bound, you're implicitly minimizing the Carroll divergence. That's it. That is why. That is called variation inference. It's a very simple idea, but it's used everywhere. Almost all the machine learning papers, I mean, not pure sampling papers, but probabilistic related machine learning papers, they all use this kind of structure to conduct variational inference. The only trick will be, okay, how do we choose Q of Z? And then given Q of Z, how do we more efficiently, more smartly maximize this lower bound? Any questions so far? Because this is very fundamental. I want everybody to feel this is right, this is reasonable. Okay. So now we can formulate the variational inference or global variational inference formulates, I mean, as an optimization problem. So suppose we're given a family S of the approximate posterior Q of Z. So it's a family of S, right? So you can view like each dot in this family as a one posterior, right? So the variational inference is an optimization problem which maximizes the variational lower bound determined by this approximate posterior in S. Right? So this variational lower bound is an integral of Q of Z logarithm of the joint distribution of your model divided by Q of Z. Right? And it can be more succinctly written as expectation of this log fraction. And usually, there's a trade-off. So the larger the family S is, the better the approximation quality, but the harder the optimization. This is natural, right? So if this is your true posterior, right? If you choose a small, very small family of the approximate posteriors, you maximize their distance. It might be easier to find the best one, which has a minimum scale divergence between the target and the posterior, but you can see that they are quite different. So it's of low quality. However, if you keep enlarging the approximation family, it's more likely you can find a better variational approximation, which is closer to the ground truth. And ideally, you might think that you choose a large enough family which can even include your ground truth posterior. And then in theory, as long as you can assume your optimization technique is extremely powerful, you might even be able to reach the true posterior. Right? But there's no free lunch. Usually, when you enlarge the approximation family, it will make your optimization harder and harder. And in practice, there's always a gap between the ground truth and your best approximation. And the current research in the variational inference is always trying to, okay, how do I enlarge my approximation family while do not mess up with my optimization? Like the recent popular approaches, or it's called gradient flow or normalization flow, is trying to use actually the random variable transformation techniques. We actually have mentioned in the class. Like you must multiply some Jacobian matrices, and if you do some kind of series of nonlinear transformations of random variables, starting the original random variables from some simple distribution like Gaussian, right? Through a series of simple transformations, because you multiply a lot of Jacobians, you'll end up with a very complicated family approximations. But your optimization itself can still be simply done by some stochastic optimization technique. This is kind of like recent work of doing that. After our introduction of the variational inference, we're gonna have we plan to have our TM to give a tutorial about normalization flow, so that you can get a better sense of that. Right now, just to give you an idea. Okay. So now we have introduced the framework of the variational inference, or global variational inference, because nearly all the variational inference follows this framework. They're trying to maximize the lower bound of model evidence, which is equal to minimizing the KL divergence. So under this framework, we're going to introduce a class of very popular and simple classical approach. It's called the mean field variational inference. So what is mean field variational inference? It just assumes the approximate posterior is factorized. So it doesn't assume, okay, the approximate posterior must be a Gaussian, must be a student T, must be whatever, some analytical form. Actually, put a weaker, I don't know if it is weaker or not, but it puts another structure in that. Okay, I don't restrict the specific form of my variational approximation. Instead, I just require they are factorized. Like, for example, factorize over each individual variable in Z. Or you can partition this because Z is a vector. Z is usually assumed to be a vector. You can partition them into groups of subvectors, and you're assuming they're factorized over different groups of variables. It's up to you. But generally, we kind of assume some factorization structure. So this Z1, Z2, ZK is just the subgroups of variables in Z, and they're non-overlapping. And each Q of Zi is a free-form distribution. We don't need to pre-specify the form. So what's the underlying assumption from this factorized form? We can see. Or what? Yes. Oh, it's not necessary ID, but it's independent. Right? Yeah, it's independent, right? They're actually assuming, okay, suppose your Z has three variables, Z1, Z2, and Z3. You're assuming Q of Z equals Q of Z1 times Q of Z2 times Q of Z3. You actually assume your posterior. I mean, it's not true posterior. Your posterior, you're assuming, okay, those three random variables are just independent. But unfortunately, in most practical applications, the posterior won't be independent and factorized over this random variables. So you can see that it's still kind of like a very crude, very strong approximations. So now, let's see if we make such kind of some assumption, which is called mean field assumption. How do we optimize or obtain each Q of Zi? So, and we can just look at the variational lower bound. Right? The variational lower bound is Q of Z times logarithm, the joint distribution over Q of Z, right? And in under the mean field assumption, we assume Q of Z is factorized over Z1, Z2 to Z and whatever, right? And also this factorized form should be put in this denominator. Right? So, and there is one simple and convenient approach to optimize each Q of Zi. That is called alternating optimization. The idea will be, okay, since I assume Q of Z is just the product of Q of Z1, Q of Z2, Q of Z3, and so on, right? So each time I just pick up one factor to optimize, while fixing all the others. Once I optimize this, I gotta fix this one, I switch to the second factor, and fixing all the others, I'll optimize it. And continue until I update all the factors, then I finish one iteration. I just keep doing this until convergence or the maximum number of updates have max number of iterations are done. And the good thing is that What?
Since they are positive, we can
Yeah. Yeah, actually, we will see that there is a form, the general form of updating this. I will see it right now. But the idea is just this alternating update. So now let us see if we perform alternating update of the factors in our mean field variational posterior. What should be the form of the update? Right? So we take some particular factor like Q of ZG as an example. When we update Q of ZG, we're assuming all the other factors are fixed, like Q of Z1, Q of Z2 to Q of ZG minus 1, Q of ZG plus 1 to Q of ZM, whatever, are fixed, right? And then we want to maximize the evidence lower bound with respect to Q of ZG only. So if we look at the evidence lower bound here, and we just make some simplification. Right? So first, this log fraction can be written as of log numerator, which is the log joint probability, subtracted by log denominator, which is log. I'm gonna write down explicitly log product of these factors, right? And remember, because we are only caring about the updates of Q of ZG, right? All the other are fixed. So for any factor other than G, right? So if you take log of Q Z G plus 1, and you do the expectation, right? Because this guy are irrelevant to this guy. So the integral is just becomes a logarithm of Q of ZG. So you can just throw out because it's constant to Q of ZG. So the only thing left, which are critical to optimize Q of ZG, will be just the Q of ZG logarithm Q of ZG dZG. Any question? Mm-hmm.
You said since QRC can be proposed product of QRCI, we can separately maximize each of them.
Yes.
This is true that each of them are positive.
Yeah.
Otherwise, how do we show that QRC log each of that term are positive?
Well, you can put some constraint on that. But when you do the optimization, you see that they're indeed positive.
Okay. At the end, it's market. So at the end, you might reach something which is not the truth, which is not the truth to maximum. Because if some of them are negative,
Yeah. I mean, if you at the beginning you set all of Q as ZG to be a valid distribution, that means they're all non-negative, right? And you do this alternating update, you always you will always get a valid distribution.
you're trying to maximize L of Q.
Yeah.
Each term and that equation must be positive.
Yeah. Each term, I mean, each term in Q of Zi must be positive. It does not mean L must be positive.
I mean, you're trying to maximize L of Q.
Yeah, maximize L of Q. That's the problem.
Each term of L of Q should be positive, not Q of C. Q of C times log P of X and Z over Q of C should be positive. That's it.
Why do you think that must be positive? It's not guaranteed. Yeah, you can look like this, right? So this guy is not necessary to be positive.
Okay, so how do you get guarantee that you will reach to the maximum? Because some of them might be negative.
Must be negative.
Might be.
Yeah, but you are upper bounded by something. Right? Yeah, you have some upper bound, which is finite, and that's it. it's not necessary, I mean, to ensure that the whole bound must be negative or positive. Yeah, remember in general, it's a log density. A log density can be positive, can be negative. It depends really on the density, the value of the density. So yeah, let's so if we keep doing this, right, keep simplifying this procedure, we know that when you take a logarithm of this product, and we only leave those terms related to Q of zj, which will only be this integral of Q of zj, logarithm Q of zj, dzj, right? And in the first part, where this product times logarithm of the joint probability can be further written as Q of zj with the product of all the other factors, right? And the logarithm of this joint probability. So if you can take a look, the K assumption of the mean field approximation is that, okay, ZG and all the other group of variables are independent, right? So that means you can do this expectation first, which essentially is to take the expectation of the log joint probability under the posterior of all the remaining variables, which we call it Q of Z not G. Q of Z not G is just the Z excluded with ZG excluded. So now we can see that, oh, by the way, Q of Z not G is just here, as we define here. So now we reach to a form that, okay, your L, your evidence lower bound, is Q of ZG times some expectation under Q of Z not G, and logarithm P of X and Z subtracted by Q of ZG times logarithm Q of ZG and DZG. Of course, we have DZG here, right? I just copy the two terms here. Okay. We want to maximize L with respect to Q of ZG. So what's the next step? So first, we should be aware that this guy can be viewed as function of ZG, right? So remember the log joint probability, and the little random variables include ZG and Z not G. Right? I have do the expectation with respect under Q of Z not G. That means all the Z not G have been marginalized or integrated out. So this expectation now is a function of ZG because ZG is still free, right? We're not taking any expectation over ZG here, right? So now that it's a ZG, we can consider to normalize it. We can consider normalizing. First, you can see that in the second term, it has a form of logarithm of a distribution. Right? So I want to turn this guy as a logarithm of some distribution as well. So to do that, you can just take a logarithm and take exp of this. Copy this guy here. We just take exp and take the logarithm, right? And this guy now becomes positive always, right? And then we can introduce some normalization constant, right? I can divide it by some normalization constant. Let me denote by big T, right? So ensure that the whole integral of this guy is 1, right? So then it becomes a valid distribution. Let us denote it by P of VG. So now if you look back at this L here, we have a Q of Zj times logarithm of P tilde Vj dZj subtracted by, just copy the second line here, Q of Zj times logarithm of Q of Vj and dZj, right? And remember, the normalization constant is just the integral of this exp stuff over z of g. So it has nothing to do with zj as well. So you plug in this normalization constant, it is equivalent to adding one more constant into this L. It doesn't matter. So now you merge the log. It is P of Zj over Q of Zj, EZJ, right? You just fraction, right? Of course, this guy is, if you just flip the denominator and the numerator, it becomes Q of Zj. Logarithm, you put Q of Zj on top and then P tilde Zj and B of Zj. What can we observe? Yeah, the maximum is 0, right? Because this guy is a KL divergence. The maximized L is equivalent to maximize negative KL divergence between Q of Z and P tilde of Q of Zg, P tilde of Zg, right? And of course, you should make your Q of Zg equal to the P tilde of Zg to make this maximum to make this objective value to be 0. Right? Does it make sense? And then our goal becomes, how do we normalize this guy, right? That's how we update Q of Zg. So this guy is actually written as here, right? So the XP, you take expectation under Q of Z not G and logarithm of the joint probability. Your Q of Zg, your optimal Q of Zg should be proportional to that. That means if you really want to get the posterior, you should do the normalization over this guy. That's your update for a particular Q of Zg. And once you update Q of Zg with this form, and then let us assume this form is analytical, is easy, right? And you can fix Q of Zg, you switch to Q of Zg plus 1, right? It has a similar form. It has a similar form, but because the expectation might change, right? You might end up with different distributions or the same distribution with different parameters. Right? So just keep doing this, and until you finish updating all the Q of Zj's. You finish one iteration, and you keep doing this until you finish all the iterations. This is coming field. Yeah, that's a good question. We're going to illustrate from some concrete examples. But I want to stress on that. So if you assume, okay, all those distributions are normal, are not weird, you're assuming this guy is easy to compute. But there are cases where you cannot compute this form. I mean, the expectation of Q of Z not G of this logarithm joint probability, you might still don't have an analytical form. In that case, you cannot apply mean field variation inference. Okay? But in many cases, we can do that. That's why mean field variation inference is quite popular, but it's not like address all the problems once and for all. Okay. So before we reach to take a look at some concrete example, let us look at the algorithm framework. So mean field variation inference is executed in following ways. Right? So we're going to first choose a factorized posterior form Q of Z, factorized over several groups, several subgroups, variable Z, right? And you can do it individually, right? Q of Z1, Q of Z2. You can also separate them into different blocks or different groups and put the factorization. It's totally up to you. And then we're going to repeat the following update procedure. Right? So we're going to go through each factor in its product. And then each time to update Q of ZG, we're going to fix all the other factors. Then our updated posterior of ZG is proportional to first take expectation of QZ not G over the log joint probability, and then take the XG. Of course, you need to normalize it to get a reasonable, to get to the correct distribution. That's Q of ZG, right? And then you move on to next G, and you fix all the others and do the same kind of update, and keep doing that until you finish updating all of the factors in your mean field variational posterior. You finish one iteration, and you go to the next iteration. You keep doing this until the change of each factor is little, or you have finished the maximum number of iterations. So any questions so far about this algorithm framework? Everyone is comfortable with that? Any question? Okay. Okay, so now let us look at a concrete example to showcase how we do the mean field variation inference in commonly used probabilistic models. Here we just use a simple variational linear regression. Okay. So this is our graphic model. So first of all, we're going to sample our parameter alpha from a gamma distribution. So this gamma distribution is parameterized by A0 and B0. And the given alpha, we sample W from a Gaussian distribution. And here we can see that alpha serves as the precision of your Gaussian prime, right? Precision or the inverse variance. We know that the gamma distribution is the conjugate prior to the Gaussian likelihood when you use your alpha as the precision. Okay. This is something we have discussed previously. Okay. And then given the weight vector W, we're going to sample each output Tn from another Gaussian distribution. Right? And this is a linear form. And the mean is W transpose of the input vector phi n, and the variance is beta inverse. So beta inverse is another is a hyperparameter. Of course, we can assume beta as a random variable so that you can assign another gamma distribution. All the updates kind of similar, but here we for conciseness, we just assume beta here is known. We just look at how do we estimate posterior distribution of alpha of W. Okay. So first, we can write down the joint distribution, right? The joint distribution of the alpha of the weight vector W, and also we observe the observations T, the response variables T. So we just multiply the prior of alpha, and given alpha the prior of the weight vector W, and given W the likelihood of each observed response Tn. And our observed data, we have n observed data, which means that this T vector has n elements, T1 to Tn. Our task is to estimate or compute the posterior distribution of W and alpha given observed data T. That's our goal. And of course, if you want to compute exact posterior, even for this simple framework, it's not feasible. So we're gonna introduce some factorization, introduce some assumption. So we are gonna assume approximate posterior with the simplified form. Our simplified form, we assume, okay, my approximate posterior of W alpha is just the posterior of W times posterior alpha. So in my approximation family, we assume, okay, the posterior W and posterior alpha are just independent. Of course, it's not true. We just issue some approximation to simplify the computation. Right? And this is definitely a mean field assumption. Right? Then the question is that how do we find the optimal QW and Q alpha, which maximizes the evidence lower bound? So we just apply the general formula in our framework, right? So to update, we can first take a look at the Q of alpha. Right? So given Q of W fixed, we'll update Q of alpha. We just know the Q of alpha will proportional to first take logarithm of the joint probability and then take expectation of this log joint probability under Q of W, then take the XP. Okay. So we can have a look at this log joint probability. And just pick out those terms related to alpha, right? Because we're trying to find a distribution for alpha. Right? For any other terms that are not including alpha, is irrelevant. You can just throw it out. So we know that P of alpha, P of T, W alpha is P of alpha itself, right? And P of W given alpha, and P of T, so T here is a vector given W. Right? So then we take a logarithm. We take a logarithm will be log P of alpha plus log P of W given alpha plus. Now I want to ask, which term is irrelevant to alpha? Which term doesn't use alpha at all? The last term, right? So given W, how we sample the observed response is just a Gaussian, right? It's here. It's here. It doesn't contain alpha at all. So that means we will take expectation with respect to Q of W. You don't need to care about this guy because this guy has nothing to do with alpha. When you do normalization, it will be viewed as constant and it will be canceled out. Does it make sense? Okay. So now let's try to take the expectation of Q of W only under log P of alpha plus log P of W given alpha only, right? Because the third term, even you take expectation because it has nothing to do with alpha, just view as constant. You take EXP, you essentially multiply that with a constant, right? So we normalize it just to cancel out. So if you look at logarithm P alpha, it's a log gamma distribution. So gamma distribution in general has the following form. It's proportional to alpha V0 minus 1 V to the power of V0 times alpha. Something like that. And of course, there are some normalization constant. Again, because this normalization constant has nothing to do with alpha, we can just throw them out and then just merge the terms regarding alpha. And finally, we'll talk about how to normalize it. Right? So here, we will take logarithm of the gamma prior. We just give you V0 minus 1 log alpha plus one B0 alpha, right? And we can take a look at this. So remember, P of W, the alpha is Gaussian, right? The Gaussian with zero mean, the alpha inverse times I, right? I'm just copying the term here, right? So you take a logarithm. Remember, you'll have a 2 pi alpha inverse I determine exp minus alpha W transpose W, right? It's just the Gaussian density. And they take a logarithm was log determinate that will give you this one minus half. It will give you d over 2. D is the dimension of W. Log alpha subtracted by log exp is just cancelled. Right? This is just log determinant of this is a log the determinant of 2 pi alpha inverse I times to the power of minus half. So it's just the standard formula of the Gaussian distribution. If you take a logarithm, this is scalar inside the matrix, so you have to take power of the dimension of that matrix. So now you end up with log P of W alpha is half D log alpha subtracted by half alpha W transpose W. Right? Remember, we're gonna take expectation of these terms under P of W. So that means you need to take expectation here. Right? And all the other terms, because it doesn't contain W, it's just constant. So now you can merge the term. You can have this guy can be merged together. This guy and this guy can be merged together. So if you write down together, you get A0 plus half B minus 1 log alpha minus B0 plus half E expectation W transpose W times alpha, right? And then you take exp of this. And when you take exp of this, you find that this is actually satisfy the general form of the gamma distribution. Okay? If you take exp, it's something like, consider take exp of this guy. It's something like that alpha to the power of A0 plus half B minus 1, right? And E to the power of minus B0 plus half expectation of W transpose W, right? So from this form, you know this is gamma distribution. And the parameter is staying here and here, right? Because for any gamma distribution like here, we just put E0, B0, but you can put it C and D, whatever. And then you must have a term alpha to the power of the first parameter subtracted by 1. The second parameter is in the power of the exponential B0 times alpha. Right? That means that through this form, right, we can identify this updated Q alpha will be also a gamma distribution and parameterized by this guy and this guy. We can denote the parameters by a n and b n. So they are A0 plus half D, right? And B0 plus half expectation of W transpose W. You don't need to do explicit normalization because once you know your unnormalized distribution contains the terms, one is power of alpha, the other is exponential to the alpha, you know this is gamma distribution.
So we should be hopeful that the layers that we find for the solution to, we can compute the values.
Yeah. Yes, yes, exactly. Of course. And actually, you made two assumptions. First, you're able to compute the expectation here, right? Second, you're assuming after you take expectation and take exp again, it will reduce to some distribution of the knowing form, so that you can get that distribution, right? Yeah, that's the basic assumption about mean field. If it turns out that these assumptions are broken, then you can now come back to mean field. Does it make sense? And now, in our case, like there is no linear regression, we're happy to find that, okay, as long as we are able to compute the expectation of W transpose W, we know that the updated Q of alpha will be gamma distribution. You just update the parameters in this gamma distribution in this way, right? Then the remaining thing is how would I compute the expectation of W transpose W? That then is reduced to update of Q of W. And Q of W, if you follow the same way, you'll see that it's actually a Gaussian distribution. So it's a Gaussian distribution, then it's very easy to compute the expectation of W transpose W. Right? So I'm not gonna repeat this again, but I will request you guys to do this manually, so you get a sense how you end up with the Gaussian. But anyway, when you do this, you will see that it will be some terms like W transpose some term and subtracted by W transpose sigma W. You can see that there's one linear term, one quadratic term. So it's actually the typical form for a Gaussian distribution, right? And then you just use completing the square trick, you can get the mean and the covariance. We have discussed this before. So, but when we compute the updates of Q of W, which we know is Gaussian distribution, of course, we need to compute some expectation of something, right, on the Q of alpha, right? So here, it will be the expectation of alpha itself. And good thing is that for a gamma distribution, the expectation of alpha is just the first parameter divided by the second parameter. We even do not need to memorize that. You just check out the Wikipedia. And usually these commonly used moments, they have all giving you the analytical form. You just apply it. So now we can just alternatively, we can just do an alternating update of Q of W and Q alpha, right? One is Gaussian, one is gamma distribution. When you update the gamma distribution, you need to leverage some expectations under the Gaussian distributions. When you update to the Gaussian distribution, you need to leverage the expectation under the gamma distribution. Keep doing this until convergence or the maximum number of iterations are done. Okay, does it make sense? Okay. Yeah, go back to the question you guys asked before, right? So make assumption that your mean field update, that is, when you fix Q of W up to Q of alpha, you're assuming Q alpha corresponds to some distribution of the knowing form, right? And of course, you also assume the required expectations are feasible to compute. Okay? And in what kind of distributions and families who can guarantee you this? That will go back to the exponential family. Okay. So we'll look at this in an exponential family. As long as your prior, like here we're assuming, okay, we got your latent random variable eta, and given your latent random variable eta, you generate your latent random variable z and x together. And in general, as long as your prior of eta is conjugate to the distribution over z and x, then you perform the mean field variational inference, which you factorize q of eta and q of z, it always gives you an analytical form. The reason is just because the conjugacy between the prior of eta and the likelihood or the distribution given eta of z and x. So here I just give you the conjugate prior of eta, right? So this you guys have seen this before. So so you're assuming x and z given eta follow some exponential family distribution. That means eta here serves as natural parameter, right? And u, x, and zn is your sufficient statistics. And then eta, which is natural parameter, if you want to have a conjugate prior, it should have this form. So this f is kind of other functions separated from this exponential family. So you must have this g eta. G eta is a normalization factor to some power of freedom mu 0. You have e to the power of this guy. So, and now if you just multiply them together, you get your joint distribution. Just apply the mean field variational approximations and try to update q of z and q of eta. You'll find that q of eta will still fall the category of the conjugate prior, with only the change of the parameters. And q of z will also be in the exponential family. And of course, your natural parameter will be changed, and natural parameter will be the expectation of eta. So we're gonna give a closer look at this. We're gonna show how this is correct, but it's relatively easy. I will encourage you to try to manually derive this by yourself, and we can do a quick review in the next lecture. Okay, thanks. Let's stop here today.